Hey, good afternoon. So today we'll be continuing our discussions on caches. So where we left off last time was some terminology. We talked about heat rate, heat miss, access time. Now let's continue where we left off last lecture. So in modern computer systems, you usually have a hierarchy in your memory. So it starts with the fastest storage medium next to the processor, which is the register. After that, you have your L1 cache, L2 cache. Your system could have different levels of cache, and the the last one is called usually last level cache. From which we're going to go then to main memory. Usually main memory is used as a cache for your permanent storage, which could be your SSD, for example, and then you could potentially use your SSD as a cache for your disk. Now, we're going to talk about using memory as a cache for secondary storage in the next lecture. Which we'll talk about paging. But at this during this lecture, we're going to talk about using these guys, last level caches. Sorry, the processor caches as a cache for main memory. So this is a topic that we discussed previously. As you get closer to the processor, the amount of storage you have decreases, but then the speed increases. So your registers are in orders of hundreds of bytes, but they're very fast. But then your SSD is much larger, but then it's slower. Using registers, usually the programmer doesn't have any say, unless they're writing assembly. Usually what manages registers is the compiler. So most programmers program in high-level languages, and then the compiler is in charge of taking your high-level program and then turning it into code that is understandable by the hardware. And in the process, it will use the registers. Hardware manages the caches. So these are usually called microarchitecture features, and the programmer doesn't have any idea about their existence. So whenever you're coding, you usually don't care or don't know how much cache your system has. The more cache your system has, the faster your program executes usually. But this is managed by hardware, and it's hidden and transparent to the user. And then the software, in particular operating system, is in charge of managing memory, managing SSD, and basically your permanent storage. This part happens with your file system, and then this happens with paging. All done by the operating system. If you look at the model that we just saw, you see that you have different levels of caching. In this case, the area that each box occupies basically indicates how much capacity that storage medium has, and the smaller it is, the faster. Now, we're going to make a definition. We're going to say miss time, basically the time that it takes to go and fetch the data that is missed at level X, is equal to the average access time at level X plus 1. So if I miss in memory in M1, I'm going to go to M2. So the miss time for M1 is the average access time at M2. Now, given that, if we're interested in average memory access time, calculated from the CPU, or basically seen by each individual instruction. Basically, that would be, by definition, the average time at M1. Now, average time at M1, we have the definition. It's going to be hit time plus miss ratio times miss time at M1. But then we can just expand the miss time at M1 using average time at M2, and then expand average time at M2 by hit time at M2 plus miss ratio at M2 times miss time at M2. And we can just keep going with this model, right? Now, take miss time at M2 and then substitute that with average time at M3. Now, when you're designing a cache, there are certain questions that you have to answer. Now, let's set up the setting here. This is an example that we're going to look at in multiple slides. Let's assume that you have a memory with 32 bytes. And let's assume that your cache is only 8 bytes. Now, in this example, we're assuming that the block size is just 1. So each block is a single byte. If you remember from the previous lecture, it's usually not the case. Usually each byte is multiple, each block is multiple bytes. But for the case of this example, let's assume that each block is 1 byte. So physical memory has 32 bytes, and my cache has my cache has 8 bytes. So it's like 1/4 of the memory capacity. Now, let's assume that the CPU accesses this particular address, 01100. Now, the first question is, how can I know if this the data is cached in my cache? Where should I look at? The second question is, let's assume that I look it up and it's not in my cache, and I want to bring it up to my cache. Where should I put it? Now, these two questions are related, obviously, because wherever you put a data is where you should be looking at that. So we'll see that these two questions are very related. So if we have an answer for one, we have an answer for the other one. The third question is, let's assume that the cache is full and we need to evict 1 byte from cache to put another byte in. Obviously, the cache has only 8 bytes, but the memory has 32 bytes. So there is no way I can fit in 32 bytes in 8 bytes. So at some point, cache is going to get full. We're going to evict someone to bring someone else in. So the question is, which one should I evict? And again, this question is also related to the first two questions because you know, you're going to evict from where you're going to put it. You can't. You sometimes don't have options, which we will talk about. Okay, so let's start with one of these questions: where to put a block in cache. The answer to that question is, usually we divide the cache into sets. Now, each set has a certain number of blocks in it, and we're going to map each memory address to a single set in our cache. So every single memory address is mapped to one and only one set. Now, the number of blocks in each set is called the set associativity of the cache. So if I have an m-way set associative cache, it means that each set has m blocks in it. Now, for example, if each set has 4 blocks, then I have a 4-way set associative cache. A fully associative cache is a cache with a single set. So there is only one set. Therefore, all blocks in the cache belong to the same set. And all addresses all memory addresses are mapped to the same set because there is only one set. The other point in this spectrum is a direct map cache where each set has only a single block. So there's only one block per set. The number of sets in the cache is equal to the number of blocks in the cache because each block corresponds to a single set. In this one, every single memory address is mapped to a single block in cache because each block is a set and each memory address has to be mapped to a single set. So each memory location is mapped to a single block. Now, if I compare these two different points in the spectrum, fully associative cache is very flexible because each memory address could go anywhere in the cache because all the blocks belong to the same set. So every memory address could go anywhere in the cache. With direct map cache, each memory address is mapped to a single block. So I don't have many options. Now, with fully set associative cache, the downside of this flexibility is that I will have longer accesses because I will have to have more hardware logic to search for my block, right? Because my block could go, my memory address could go anywhere in the cache. So I will have to search the entire cache to see if I have my data. That means that I need more hardware logic to do this checking. So this means that I'm going to have a slower cache. With direct map cache, I don't need many hardware because I only need to check with a single byte to see if my data is there. So it's less flexible, but a lot more faster. Let's look at direct map cache. Now, as I said, with direct map cache, every single block is a set. So in this example, because each block is 1 byte, therefore we have 8 sets: set 0, set 1, set 2, all the way to set 7. So each block is a set. Now, how do we do the mapping? Well, because we have 8 sets, the way we're going to map from addresses to sets is that we're going to need the last 3 bits of our address to find the set for this address. So if I look at the last 3 bits of my address, that could tell me which set this address is mapped to. Now, any address with the same 3 last bits are going to be mapped to the same set. So for example, in this case, all the addresses that end with 100 are mapped to set 3. Now, that's fine. So let's go back to the questions that we have. So let's assume that let's assume that I want to look at this address. So let's say I want to check my processor produces this address. Now, if I have a direct map cache, I know where to look at. So I have to look at this address, this particular block, because the last 3 bits match. So that's okay. Now, how do I know which one of these guys, this one, this one, this one, or this one, I have cached? Because all 4 of them are mapped to the same block. How do I know which one I've used? Well, I don't have any way to know other than tagging these so that I can check. For the tag, I'm going to use the last 2 bits to tag my data. So each cache has the data. For example, this might be D3, this might be D2, this might be D1, and D4. So in this cache, if I have D1, then I'm going to tag it with 11. If I have D2, then I'm going to tag it with 10. if I have D3, then I'm going to tag it with 0, 1. And if I have D4, I'm going to tag it with 0, 0. So that's the idea of tagging. That way, I can just know which data I'm caching. So basically, that's the idea behind tagging. We're going to add tag, and then for D3, for example, in this example, I'm going to put 0 and 1 as a tag. So now let's look at fully associative cache. With fully associative cache, we only have a single set. All the bytes, all the blocks belong to the same set. So I have only a single set, S0. And this means that every single address could go anywhere in the cache because all the bytes belong to the same set. Okay, so this means that I have to search all of them. Now, you know, if this is the data, this is D, let's say D, what is the number? This is 12. Is that 12? This is 8 plus 4, 12. Doesn't look like 12. No, actually, it is 12. So D12. How do I know where this data is? How do I know where to find it? Well, it could be anywhere, so I have to search all of them. To do this search, I need to, again, tag them. Now, what do I use for tag this time? Well, I'm not using any bit of my address for finding the block, so I can use all the bits. Indeed, I have to use all the bits of my physical address to tag tag my data. So wherever I put my data, because it could be anywhere, I'm going to use the address for this to tag my data. Now, whenever I'm searching for a specific address, I have to just search and see if I have that address in my tag. And if I do, then the corresponding cache line is the data that I'm looking for. And if I don't have the address as my tag, this means that the data is not cached. So it's a miss in the cache. Now, to just put everything into perspective, we discussed this direct map cache and we discussed this fully associative cache. So this is my D12. So this is address 12. Now, as we saw with direct map cache, it could go to a single memory, a single cache block, which is basically I'm going to take the mode of 12 to 8 because I have 8 sets. So I get the address, I do the mode 8. This is basically getting the 3 last bits. So this is equal to 3 last bits. That gives me the set number for this particular example. With fully associative cache, it could go anywhere, right? With two-way associative cache, it means that each set has 2 blocks. So basically, I have block 0 for each set and block 1 for each set. Now, because I have 8 blocks, this means that I have 4 sets. So this is set 0, block 1, set 0, block 2, set 1, block 1, set 1, block 2, all the way to set 3, block 0 or block 1, and set 3, block 2. So this one, I have 4 sets. So I have to get the mode of 4, which is equal to last 2 bits. To find where to look at. Now, once I find the set, so 12 mode 4 is 0, so I'm going to look at set 0, but then set 0 has 2 blocks because it's a two-way set associative cache, so I have 2 options. Now, where is it? So I have to look at the tag, and the tag is everything left of the address. Whatever you used for the index, the rest of it you're going to use for the tag. So with With direct map cache, I'm going to use 3 bits for index, so the last 2 bits are going to be used for cache. With two-way associative, I'm going to use 2 bits for index, so the rest of them, which are the 3 bits, are going to be used for tag. For fully associative, I'm not going to use any bits for index because there is only one set. So all the bits are going to be used for tag. Now, in general, your block is more than a single byte. So you have a block that is 32 bytes or 64 bytes or 128 bytes. Now, the number of if you have a block that is more than a single byte, then you have to know which byte you need. So this is going to be, you need some number of bits. This is going to be log 2 of block size. So if block size is 1, which is in the previous case, then you don't need any bits to find your bytes because there's only 1 byte per block. If you have 32 bytes for each block, then you need 5 bits to address each byte in your block because your block has 2 to 5 bytes. And remember, each load or store is for a single byte. So you're going to just pick the byte that you want. For that, you need log 2 of your block size, number of bits. Now, when it comes to index, it's going to be, you're going to need log 2 of number of sets. So the more sets you have, the more bits you need to find the set that you need, and then the rest of it is just left for cache tag. Whatever is left is going to be your cache tag. So that's that. Okay, so let's look at direct map cache. Let's look at this. So let's assume that my block size is 32 bytes. This means that I need log of 32, which is 5 bits. So 5 bits are going to go for byte select. Now, in this example, I'm assuming that my cache size is 1 kilobyte. So I have 2 to 10 bytes. Now, each block is 2 to 5 bytes. So how many blocks do I have? I have 2 to 5 blocks. Now, because this is a direct map cache, this means that I have 2 to 5 sets, because each set has a single block. So I have 2 to 5 sets. So log of that, log 2 to 5 sets, that's 5 bits I need for finding my set. And the rest of it goes for tag. So in this example, I have 32-bit address. So 32-bit minus 10, that's 22 bits left for the tag. So the way it's going to work is I'm going to use my cache index to find the set. And once I have found the set, I'm going to find the byte in that set that I need. So I use the byte select to find the byte. And then I have to check the cache tag to see if I have missed, I have hit in the cache or I have missed in the cache. Now next, let's look at set associativity. Let's assume that I have let's look at an example where I have a two-way set associative with the same example. So if I don't change the number of bytes I need for each block, then I'm not going to change the number of bits I need for my byte select. So that's 5 bits like before. Now, because I've changed it to two-way set associative cache, so previously we saw that we have 2 to 5 blocks. Now, each set has 2 blocks. This means that, so this is block per set. So this means that I have 2 to 4 sets. So I have 2 to 4 sets, and therefore I need 4 bits to select my set. It's the log of that. And the rest of it is going to go for my tag, which is 23 bits. Now, the way it's going to work is I'm going to use, as before, my cache index to find the set. So now I have 2 different blocks. So these are all the block zeros or ones, and this is block 2 for all sets, right? So these are the number of sets, and these are all the block ones, and these are all the block 2s. So I pick the index. Now I have to check the tag for both of them because I have 2 candidates. So I have to check the tag for both of them. And then if they're valid, if this cache is valid, then I have a hit. Otherwise, I have a miss. And once I found my block, then I can look at the particular byte within that block to read my data. Now let's finally look at fully associative cache. So with fully associative cache, I don't need any byte select because there is only a single set. So no bits are going to use. No bits going to be used for my set select because there's there's only a single set, so no bits for that. Again, I'm assuming that each block is 32 bytes, so 5 bits here, and the rest of it is going to be my tag, so 27 bits for tag. Now, this is going to be the most expensive hardware to search, obviously, because my data could be anywhere in the cache. So the first thing is I'm going to choose the corresponding byte using my byte select. So now it could be this byte, it could be this byte, it could be any of these bytes. So these are all the particular bytes for all the blocks. Now I have to check my tag with all the tags. And this is where the hardware is expensive because I have to check this tag with all these tags. And probably I want to do this in parallel. So this requires a lot of hardware to check tag for all the bytes for all the blocks in your cache. And if any of them hits, then I have a hit in my cache. Now, usually our caches are physically addressed. So we're using physical address to address our caches for the tag and for basically finding the set. Now, the program produces virtual address. So when I have the program or the process generates virtual address, then this is mapped to physical address. Now, the virtual addresses that are generated are usually sequential, right? So your program generates, if you're going through your code, the PC is going to be PC, then PC plus 4, then PC plus another 4, another 4, another 4. So the addresses that you're generating are sequential. But when you map them, there is no guarantee that the physical addresses that you're going to get are sequential. The physical addresses that you can get might not be sequential. Now, in the extreme case, you might be so unlucky that all your physical addresses that are allocated to you are mapped to the same set. So if all the physical addresses, all the physical pages that the operating system has allocated to a single process, if all of them are aligned, let's say they're all aligned, then they could all be mapped to the same set in your cache, or like 2 or 3 sets in your cache. Now, as a result of that, this process cannot use the entire cache. So even if your cache has, hundreds of sets, if all my physical addresses are mapped to a particular set, then I'm just going to be using that particular set. So I will have a lot of conflict in my cache because all of them are going to be mapped to the particular set. So the rest of the sets are not going to be used. And this is going to be super bad for my application. Now, to avoid this, the technique that we use is called page coloring. Now, what is page coloring? So page coloring says, look at the number of sets that you have in your cache and assign a single color to each set. So this is my cache. So I assign a single color to each one of my cache sets in my cache. Now, I look at all the physical pages that are mapped to first set, and I assign the same color to all of them. So as you can see, all these red ones are mapped to the first set. So I will color them all red. All the orange ones are mapped to the second set. So I will color them all oranges, and so on and so forth. Now, all I need is when operating system does the mapping. So when I am populating my page table, basically whenever I'm doing the mapping from virtual page number to physical page number, all I need to do is to make sure that I'm using all the colors. So as long as I'm using all the colors for my virtual pages, so whenever I map this virtual page to a particular physical page, I use the color for that physical page. So as long as I make sure that my virtual page is colored using all the colors, I have made sure that the corresponding physical pages are not going to be contending for the same set. They're going to be distributed among all the sets. So this is called page coloring. It's usually implemented inside the kernel because the kernel is the one that is assigning the physical pages to visual pages. Now, what are the possible sources of cache misses? The one that we just talked about was this conflict miss. So this happens when your addresses are mapped to the same set. So they have to compete for all the blocks in that set. And then they could cause conflict misses. Now, to solve this, you could increase the size of your cache. If you increase the size of your cache, then you will increase the number of blocks per set. Sorry, then you will have more sets. Then you will have less conflict because the more sets you have, the less number of memory addresses are mapped to each one of them. So you will have less conflict. Or you can increase the set associativity of your cache. So you can have more blocks per set. That way you might have less conflict misses. Now, the other ones are, the first one is compulsory. So these are the cache misses that happen when you start using a single address that you haven't seen before. So obviously, if you haven't seen an address before, the chances are high that you cannot find that in your cache because you haven't needed it in the past. So these are called cold misses as well, and there is usually not much we can do. One thing you could potentially do is to prefetch. So prefetching is something that you could do. So when you access a certain address, you can prefetch addresses close to that, so that even though you haven't yet accessed those addresses, you're guessing that in the future you're going to access them. So you could prefetch them. But that's pretty much all you can do. Then you have capacity misses. So this is when, it's just because your cache is small, you are going to evict someone to bring someone else. So the solution to this is to just increase your cache. Obviously, if you increase your cache, you're going to make your cache slower. The other one is the coherence misses. So these are the misses that happen because of cache coherency protocol. So if you remember when we were discussing cache coherency protocols, we said that, if somebody requests, for example, to have access and shared, in a modified state, then everybody else should invalidate their caches. So when they invalidate, then next time they need that address, they're going to have a miss, which is caused by cache coherency. Okay, now when it comes to replacement policy, so let's say I have found the set corresponding to this address, and I have a bunch of options. So if I have a direct map cache, then I don't have any options. So there is only a single block for this set. So if the tag for this block doesn't match the tag for my data, I have to evict this and bring my new data. There's not much we can do, right? There's no replacement policy because we don't have any option. Now, if I have set associativity like 2-way, 4-way, 8 ways, this means that I have more than one option to evict. So if all of them are full, then which one of the blocks am I going to evict to put the new one in? Now for that, I can randomly choose. I can randomly evict a page, evict a block, and bring the new block in. With random, the downside, it's easy to implement, but the downside is you might actually evict a block that is really used. So if there is a single block in your cache that you're constantly using, with this random eviction, there is a chance that you actually evict that block, which is bad. So you don't want to do that. So the other option that you have is to evict maybe the least recently used one. So you look at when was the last time you used a block, and you pick the one that was used least recently. Now we're going to talk about different replacement policies later on when we talk about paging. So when we are talking about paging, we're going to talk about using memory as a cache for hard disk. So in that case, we are also going to pick a page for every page that we're bringing in. We have to evict a page if the memory is full. And then finding that page requires some replacement policy. Again, in that case, you can randomly select another page and evict it, which is really bad. So we'll talk more about replacement policies when we talk about paging. Okay, now the next topic that we have to discuss is what happens on a write. If you write to an address, what happens? Now there are two possibilities. When you write, you could write to both cache and memory. So this is called write through, because the write goes through the cache and also it goes to memory. So the write happens in both memory and cache. There is also write back. So in write back, you just write in cache and you don't write in memory. Now, eventually you have to write in memory, but when you're going to write in memory is when you want to evict this block. So as long as this block is not evicted, you can just keep writing to the cache. The moment you want to evict this block, you have to write the result of your the last update to memory. So this is called write back. Now with write back, so let's first look at the upsides of write back and downsides of write back. So with this one, we're avoiding repeated writes to DRAM, right? Because you could be writing a lot to a single address, but none of them is going to go to RAM. all of them are going to just change the data in cache, which is a lot faster than memory, right? If I have to go to memory, I'm going to spend a lot of time. If I'm just going to be hitting in cache and writing cache, it's going to be a lot faster. So this is going to be fast. And then eventually I'm going to write the last update to my memory. So I'm saving a lot of memory activity. The other upside of this is that for every write, I don't need to wait for memory. So with write through, I'm writing to cache, which is fast, but I also have to write in memory, which is slow. So I have to wait for that write to happen so that I can continue. Whereas with write back, it's not the case. Now, what are the downsides of write back? The first downside is it's more complex because you have to add a lot of logic to track which blocks are written to, and we have to have a logic that would then, in the time that you're going to evict this page, this block, it's going to go and write in memory. So more complex. The other one, the other difficulty with this one, or downside with write back, is that when you have a read, it could cause a write back because your read could require a replacement. Maybe the address that you're reading is not in the cache, so the cache is full. So you have to evict a block to put this new block. Now, if it turns out, if it happens that the block that you're going to evict is a dirty block that you have been written to, then you have to write it back to memory. So a read resulted in a write because of the write back mechanism. This doesn't happen in write through. So in write through, no read would lead to a write because all the writes have happened before. So whenever I had a write, I also wrote it in the memory. So I can evict any block I want without doing any extra work because I've already done that work. So a read miss is not going to cause a write back. But then the downside of write through is that we're going to keep the processor hostage for every write because it not only has to write in the cache, it also has to go and write in memory. Now, here's where we're going to go back to the discussion of address translation. We're going to, now that we have talked about caches, we're going to go and see if there is any way we can use the idea of caching for address translation. Now, what is the problem with address translation? So the problem with address translation is for a single memory access, my processor is going to produce a virtual address. So if, let's say, I want to read a memory location, the process is going to generate a virtual address. Now, this virtual address, let's say I'm running in an x86 64-bit system, this is going to result in 4 reads to just translate the virtual address to physical address. So I have to do 4 reads. I have to go to page table level 1, page table level 2, page table level 3, page table level 4 to eventually get the physical address that I need, so that then I can go to my page, my memory, and read the data that I needed. This is very expensive. And once I translate the next address, I have to translate again. Now, the idea is very similar to the data that we cache. So we cache the data from memory in our caches. We can also cache the translations. So if I translate a single virtual page number to physical page number, if I know this translation, I can save this in my cache. So if next time I need the same translation, if I need to know what physical page I need for a specific virtual page, I can first look at my cache and see if I have translated this before and I have cached it. If I did, then I don't need to go to my page table and do the 4 levels of page table walk to get the translation. I just have it. So the idea is, although page table is here, what if I can just cache my translations close to the processor so that I don't need to go to my page table, and I can just look at my cache and look at the translation and find it there. Now, this is an idea that is almost universally implemented in all our modern processors. It's called the cache that is used for caching virtual to physical address translation is called translation look-aside buffer, TLB. So if you hit in TLB, this means that you have found your translation. Congratulations, you don't need to go to your page tables anymore. If you miss in TLB, then you have to go and do the translation. Now, we know that for our addresses, we have locality, right? Because let's say if you're looping over a bunch of instructions, you're going to have a spatial locality because you have PC, PC plus 4, PC plus 8, so on and so forth. So these are all in vicinity of each other, all virtual addresses in vicinity of each other. So if you translate one of them, you can probably use, let's say all of them are in the same page, then you have temporal locality because next time you're going to look at the same page, right? You could also have a spatial locality. So if you have a long array that fits into a bunch of physical pages, then virtual pages, then you have a spatial locality for your virtual addresses as well. So we know that we have locality in our addresses. Therefore, we can use that locality in our translations. So the idea is, instead of getting our virtual page and go to page table directly, I first go to my TLB to check if this virtual address has been translated. If so, good. Congratulations. You don't need to do anything extra. You already have found your physical address. Just go to physical memory and get your data. If not, then you can go and search your page tables to get the translation. And if you find a valid translation, then you can just cache it in your TLB because you didn't have it. Now you have it, so you can cache it. And if you find an invalid address, then you raise an exception. Now, the TLB is going to be a cache for page table. So I have a page table entry. In my page table, I'm going to cache that here. It's not going to be exactly the same, but I'm going to just say PTE. So I'm going to cache these page table entries in my TLB. OK, now let's assume that operating system is reducing the access of a single page. So for example, there was a page that processed this single process had a read and write access, and now operating system is reducing the access to just read only. So the operating system knows about PTE. It goes and and sets the W bit to 0, says, OK, this doesn't have write access anymore. Now, what should happen to the TLB? Because if I don't change the TLB, this TLB has this write a bit set to 1. So if my process tries to store something to this page, it's going to be granted because I'm not going to go to my page table. I'm going to hit in TLB and be done with it. So if you're reducing the permission, you need to disregard the corresponding entry in TLB. You have to say this entry is no longer valid. You cannot use it anymore. Now, in early computers, there was no way to address individual page table entries in your TLB. So you had to flush your entire TLB you have to say, okay, nothing in my TLB is valid anymore, flush it, and do it again. In new architecture, modern architecture, that's not needed. You can actually invalidate a single page table entry in your TLB, so that's fine. You can invalidate a single entry in your TLB. That's fine. So that's what you should be doing. So if the operating system reduces the access, then it has to go and tell the TLB that this particular entry is no longer valid. What if I add permission? What if it was read only and then I made it read and write? So in this case, you don't need to do anything actually, because in your TLB, the write bit is going to be 0. So if your process tries to access that page and write to it, the hardware is going to notice that this bit is 0, so it's going to raise an exception. And at that time, the operating system could get involved and say, no, this is fine. Update this TLB and you should be fine. Update this TLB entry and you should be fine. So we can just wait for write to happen to change the TLB. So there is no security risk if the permission has been increased. What if you invalidate a page table entry, right? So let's say you had this page and then you had your memory got full, and then you had to swap this page to your hard disk. Now, when you swap this page to hard disk, then no longer this translation is valid because this corresponding physical page is no longer used for this virtual page because I have swapped it. So in that case, the operating system is going to come and set this valid bit to 0. It's going to say, OK, this is no longer valid. What should happen to the corresponding TLB? Well, very similar to reduction of permission, we also have to get rid of that TLB entry. OK, now, as I said, the TLB entry is not exactly the same as page table entry. The TLB entry has usually less bits than page table entry. One of the bits that are not needed in TLB is the access bit. So if you remember, in page table entry, there was a bit here called access bit. So this was a bit that is set by the hardware when this page table entry is accessed. So basically, if your process reads or writes to this page and the translation is not yet done, then hardware is going to do a page table walk, find this page table entry, and then find the physical address. When this happens, the hardware sets this bit to 1. Now, why does the hardware set this bit? Well, this is a signal to the operating system, right? Because page table is maintained by the operating system. Hardware is just telling the operating system that, look, this page was used. Now, when we talk about paging, we'll talk about, and in particular, when we talk about replacement policies, we'll see that I can actually say it now. When I was talking about replacement policies, I said least recently used. So it's important when you want to evict a page to know if this page has been used or when was the last time it was used. So this is a way to know that this page was used by hardware telling you that I accessed this page. So this is a signal that the hardware is giving the operating system. Now, how operating system uses this, we'll discuss. But do I need to have this bit in my TLB as well? So this is in my page table. Now in TLB, I'm going to have a copy of this entry here in my TLB. Do I need to have this access bit? The answer is no. There's no need for that, because the first time I need this translation, when it's not in my TLB, I come and do a page walk. At that point, I can set this bit to 1. And if I have it in my TLB, this means that I've already looked in my page table and the access bit is already set to 1. So there is no point in setting this back to 1 in TLB as well. How about the dirty bit? So if you remember, there was a dirty bit as well here, which was used, again, if your process does a write to a page, then the hardware sets this dirty bit to 1, saying that this page has been written to. Again, a signal to the operating system. When the operating system wants to do paging, it's important to know if a certain page is changed. Okay, do I need to have this bit in TLB? The answer is yes. It actually matters to have this bit in TLB entry as well. So if this is a TLB entry, it's good to have this dirty bit. Now, the first time you do a write, let's say that initially you read this page. So the hardware sets this access bit to 1, the dirty bit is set to 0, and the dirty bit is set to 0 here as well. So initially you didn't write to this, it was just a read. Now, next time you're writing, right, what happens is the hardware is going to set this bit to 1, and it's going to go out to the page table and set this to 1 as well, to indicate that a write has happened to this particular page. Now, consequent writes. So this is the first time I'm doing a store. Now let's say I keep doing a store to this page. I do a lot of stores to this page. When hardware sees this 1 set in TLB, it knows that the corresponding dirty bit in page table is also set to 1. So it doesn't need to go to page table and set it to 1 again. So having this bit here helps us to avoid going to page table frequently, because we already know that we have done it. So that's why it's better to have this dirty bit in TLB. With access, it's not needed, because if I have it in my TLB, it means that I have already accessed it. So the bit is already set, so there is no usage for this bit. Now, one question that you can ask is, do I actually need these 2 bits in my page table entry? As I said, these are the bits that are used, that are set by hardware to send a signal to operating system. The answer is really not. So we're just having them to speed things up, but in principle, we don't need them. So for example, for the dirty bit, the purpose is for the operating system to know that this page was written to. Another way for operating system to get this information is to just give this page a read-only access. Now, if the process wants to write to this page, there would be a page fault, because hardware looks at the permission and sees that this was a read. So you can't write. So I'm going to tell the operating system that a page fault has happened. Now, at this point, operating system wakes up and realizes that this page has been written to. So operating system could then go and tell hardware that this is fine. You can let the process write. But now I got that signal. It's an expensive way of getting this signal, because previously hardware was automatically setting this dirty bit to 1 without waking up the hardware, without waking up the kernel. But with this method, we're waking up the kernel on every write. So again, in principle, it's possible to get this signal without this bit, but in practice, it's good to have this bit and let the hardware set it without waking us up. That way we get better performance. The same with the access bit. So you could basically make every page table entry invalid. So every time there is an access to a page, again, the hardware is going to wake up the operating system, and then operating system can get the signal that this page table entry is used. Okay, so next, let's talk about difficulties that could arise by having TLBs. the first one that we're going to talk about is homonyms. What is a homonym? Homonym is a single virtual address that is mapped to different physical addresses. And this happens when you have two different processes that use the same virtual page in their virtual address space. This could happen very frequently, right? Because each process has its own virtual address space. So they're going to use the virtual addresses in their virtual address space from 0 to whatever. So they could both have the same virtual address, but then they're mapped to different physical addresses. Now, why this might cause problem with TLBs? Well, if I only in my TLB, if I save virtual address to physical address, then after I do a context switch, the next process could use the same virtual address, but then the translation I have in my TLB is valid only for the previous process. Now that I have context switched, this virtual address should be mapped to a separate physical address. So this page table, this TLB entry no longer can be used. Now, to solve this problem, one approach is to, on every context switch, we can flush our TLB. So we can just get rid of all the entries in our TLB and then start over. So this is simple to implement. It's easy to just flush all the TLB entries, but it's very expensive. The reason it's expensive is, let's say you context switch from process A to process B and you get rid of everything in your TLB. But then let's say the first instruction that process B executes is an open file system call. So it's going to go to sleep again. So there would be a system call. There would be a context switch back to process A. Now, process B didn't use any of its TLB, and we're back to process A. But then the entire TLB is now flushed. So process A has to start over and fill up the TLB by just doing the translations. So it's just wasteful. Now, another approach is instead of just using a virtual, instead of just saving a virtual to physical address, I can tag my process ID to my virtual address to physical address translation. So this is a tag, very similar to the tags that we talked about previously. So it has a different name. It's called Process Context Identifier, PCID, but in essence is just a PID. So if I do that, then when I context switch, I don't need to flush anything because my new process has a different process identification, and it's going to tag its translations with that. So when I find the same virtual address, it has a different process ID. So this entry cannot be used for this new process. So I'm safe. So this is going to be OK. So this is the upside is that it's less expensive because we're not flushing the entire TLB. The downside is that it needs some extra hardware, right? We have to add extra logic to tag, to check the tag, and all of that. OK, now the other problem with TLBs is the same problem we had with cache coherency. So TLBs are caches for page table, right? And very similar to cache coherency problem that we saw in multiprocessors. The TLBs could also have coherency issues. Here is an example. So let's say you have been running your process 0 on processor 1 and processor 2 and processor 3. let's say that the translation for this particular virtual page for this particular process is cached in both TLB1 and TLB2. So both of them have cached this. Now let's say you're running your process right now on processor 1. So you're running P0 here. And for some reason, operating system decides to reduce the permission or I don't know, change the page table entry for this virtual page. So as we discussed, well, it goes to the page table. What the heck? What did I do? So page table, it goes to page table, it finds the page table entry, and it changes it. So that's fine. We also saw that it has to also change this TLB. It should just say, okay, this is no longer valid. But what about this guy, which is cached in another processor's TLB? So we have a problem because we sort of need to make all these entries coherent. Consistent. The way it's done is by using interprocess interrupts. So interprocessor interrupts. Processor 1 is going to interrupt processor 2, and it's going to interrupt processor 3, and tell them that if you have this particular translation, invalidate that, shoot down this particular translation from your TLBs. Now, process 3 is going to come back to processor 1, and say, okay, I didn't have this, so it's all good. Processor 2 is going to invalidate this and then send an acknowledgement to processor 1. Once processor 1 has all the acknowledgements, then it can continue with execution. But this basically means that we need to shoot down all the translations in all the other processors if we have to. So this is called shoot down, and the overhead of this increases linearly by the number of processors that we have. So the more processors we have, the more it takes time to do the shoot down, because each processor should talk to all the other processors and wait for all of them to acknowledge the shoot down before it can move on. Okay. If you don't find your address translation in TLB, you're gonna have to go to whoever is in charge of address translation to get the translation. Now, if you remember, there was a slide in the previous lecture. It was hardware versus software translation. I don't exactly remember. I think the title was this one. And in that slide, we talked about where to implement address translation. So this is exactly the same. So nothing has changed. Now it just we have added TLB. So now if you miss in your TLB, if you cannot find the cached data in your TLB, then you basically have to go to whoever is responsible for the translations to get your translation. Now, if you are implementing translation in hardware, so if you have a hardware traversed page tables, then a TLB miss is going to result in a page table walk, which is basically you're going to go through, your hardware is going to go through the page tables to find the translation. If hardware finds a valid page table entry, it's going to use it, so nothing happens, so no kernel involvement at all. If the page table entry is not valid, or if the permissions don't match, then it's going to raise exception. It's going to raise page fault exception. So kernel is going to wake up and deal with it. Now, if everything is done in software, if the translation is done in software, then on every TLB miss, you're going to cause a TLB fault. So this becomes a an exception. So hardware on every TLB miss is going to wake up the software, and then the software is going to go and find the translation. Okay, so continuing on this, now, when an exception happens, any kind of exception, if you remember exceptions, going back to the operating system concepts, exceptions were caused by the program. So they were synchronous, meaning that, for example, you have divide by 0. Your code, your process executes an instruction that causes exception. For example, divides by 0 or causes a page fault. Basically accessing, for example, a page with that is invalid, or accessing a page that has wrong permission. So at that point, when the exception happens, you're going to wake up the exception handler in operating system. Exception handler is going to handle the exception. This could lead to termination of the process, in which case the process will terminate. But it could also not lead to termination. It might be, for example, lead to expansion of heap or expansion of a stack. So operating system can just increase or reduce the permission of the TLB or whatever it has to do, and then it says, okay, it's fine, now you can go and continue. Now, when you want to continue, where should you start continuing? So usually we want to restart the same instruction that caused exception. So if I accessed a page that was swapped to disk, now that I brought back the page and now that I have a valid translation, I want to execute that same instruction. So this is fine. It becomes a little bit tricky if instructions have side effects or if you execute instructions out of order. Here I have 3 examples. So the first example is push. So if you have a push instruction, how is it really implemented? This basically is a store this 10 to SP, wherever SP is. Sorry, it's going to be a add SP and 1. So you're going to increase SP by 1, and then store your data in wherever SP is pointing to, right? So if you remember, if you look at the starter code, we have this plus SP equals whatever, whatever you want to do, right? So this basically is increase the stack pointer and then write to that address. So a single instruction is really a bunch of micro instructions. Now, what happens if you get exception here in a store 10 to SP? So you've already increased your SP by 1, and now you're executing this store and you get exception. If you come back to this one, if you come back to this push instruction, sorry, if you want to re-execute this push instruction, you're going to again add another 1 to your SP and then write. So you're going to be having 2 SP plus 1s in your execution. So it's not going to be fine, right? Because this instruction has side effects. The side effect was that you initially increased the SP, which was fine, and then you tried to write, which is when you got the page fault. Now, if you go back and do the same thing again, in effect, you have increased SP by 2 rather than by 1. The other example is out of order execution. So here I have an example. So look at example 1 here. I have a multiplication. I'm multiplying R2 and R3 and putting the result in R1. Then my next instruction compares R1 and R4. If they're not equal, then I'm going to jump to loop, which is somewhere else. Otherwise, I'm going to go and execute this load instruction. Okay, now usually this multiplication takes more than one cycle. This is usually a few cycles. Let's say this takes 4 cycles to do. Let's say I have 64-bit registers and I want to multiply them. That maybe it's going to take 4 cycles. So can I start executing this next instruction before the first one is done? No, because the next instruction, the branch instruction, needs the result of the first one, which is the multiplication. So I cannot check R1 with R4 unless I have R2 times R3. But what about this other instruction, the third one? The third one works with R5 and R6. So it's not dependent on the 2 instruction on top directly. However, it's related to the branch instruction, because if the branch instruction is taken, if R1 and R4 are not equal, then I'm not going to execute the load. I'm going to jump to loop. Now, in out-of-order execution processors, what happens is it's too expensive to wait for the multiplication to be done before we start looking at the future instructions. So what happens is the hardware is going to predict whether or not this instruction is going to be taken. If this instruction is going to be taken, so if the prediction is, I'm going to look at all the previous times that I have executed this instruction, and let's say always this instruction was not taken. So I'm going to say with high probability this branch is not going to be taken. So I'm going to start executing this load in a speculative manner. So I'm going to speculate that the branch is not taken, so I can just execute all the instructions after the branch. Now, what happens is I start running these instructions, but I don't change the register or the memory for these instructions that I'm speculatively executing. Instead, most out-of-order processors have kind of like a dummy or extra registers that they use for all these for all the speculative execution. So they change those without changing the architectural registers. If in future turns out that this branch was absolutely not taken, so once I have the result of the multiplication, I check and see, oh, this branch was actually not taken, so I was right. So in my prediction, I was right. So then all the instructions that I executed speculatively, I can now make the changes in my actual registers or go and change my memory. So now it's fine. If it turns out that no, my prediction was wrong, and turns out that this time this branch was taken and I have to go and jump to loop, then nothing has happened. So I haven't lost anything. I just, instead of waiting, I did some extra calculation, but I never changed any registers, my architectural registers or my memory. I only changed these dummy registers that the programmer is not aware of. So I can flush them. I can just disregard whatever I have done and then jump to loop and continue from loop. Okay, so far so good. Now, what could happen if this guy, this load that I am executing speculatively, leads to an exception? So what if this address that R6 is pointing to is invalid, is a segmentation fault? So this is an issue, right? Because I wasn't supposed to execute this instruction, and I started executing this instruction out of order, and then turned out that this instruction actually led to an exception. So what should I do? Now the same could happen in example number 2. I have a divide, so I'm dividing R2 by R3 and putting the result in R1, and the next instruction is a load. Now these two instructions are independent, right? So the first instruction works with R1, R2, and R3. The second instruction works with R4 and R5. So they're unrelated. So most of the out-of-order execution, out-of-order processors could reorder these two instructions. What if this instruction, I start executing it, because this divide is probably very expensive, is very similar to that multiplication. If you're dividing 264 bits, it's expensive. So if that's the case, and I start running this load and I get an exception, what should I do? I wasn't supposed to do this load. I was supposed to first do the divide and then go to the load. So if I get exception, what should I do? So this, I know I'm over time, but I have to finish this one before ending this lecture. So this leads to a concept in operating system computer architecture called precise exception. So the idea here is I'm going to keep track of all the instructions that have been executed in the program order. So if I do any out of order execution, I can still do them, but I'm not going to assume that those instructions are retired. I'm going to retire instructions in the same program order that the programmer has written. Now, if an exception happens for instructions that are speculative, I'm going to ignore them. So I'm going to only take care of exceptions that happen for the instructions that have retired. So this is going to kind of like how this could happen. It requires some advanced computer architecture class, or maybe even in your introductory architecture class they teach you. I don't exactly know, but this is not a topic for us to discuss. This happens with hardware techniques. So you make sure that you're tracking instructions based on the same order that the programmer has, and make sure that the exceptions are raised again with the same order that the programmer has written. And once you so basically, if you get an exception for an instruction that is not retired, you just ignore that exception and you wait for that instruction to retire, and at the time that it retires, then you can take care of the exception that happens. So again, I'm not going to talk more about these, but just so you know, in hardware, we make sure that all these side effects and all these out of order executions do not alter our architectural state in an out of order manner. So we just make sure that the exceptions are taken care of in the same order that the exception has happened, that the instruction has been retired. So in essence, I'm going to go through the instructions that I have in the program order. One of them is going to, if one of them raises an exception and it's its turn, then I'm going to have the handler in operating system take care of that exception, and then I'm going to go and start running that faulty instruction again, and this is going to continue. Okay, so I'm going to stop here. Thank you for sticking around. Thank you to those of you who are watching the recordings. Take care, be safe. We'll have a a makeup session tomorrow. So I'll see you tomorrow. Take care, be safe. Bye bye.